For the first graph of range versus launch angle, choose the columns to be plotted, choose Insert, and then Scatter Plot, no lines. Under Trend Line, More Options, you will want to fit the data set using a polynomial of order 2. This should give a peak for your data that you are looking for. To find the peak of this graph, make it big by limiting the range of both your x-axis and y-axis. To do this, go to Axes and then choose More Options. If you highlight the x-axis, you can set minimum and maximum values for the range of the x-axis. For my data set, I chose my minimum to be 20 and my maximum to be 90 because those values lie outside my minimum and maximum values for the angle. Do the same for the y-axis. Click on it and make its range span your data set. My data ranges from about 5 meters up to just less than 35. So I choose those values for my minimum and maximum for the y-axis. The result is that the data set portrayed in the graph becomes magnified to make it easier to judge at what angle my maximum angle and range might be. For the second and third graphs, you should get partial parabolas. Again, make sure to use Scatter Plot, no lines choice for both graphs. Make sure the graph is expanded to full page size and use a polynomial fit to each. You should extend all fits for these two graphs toward the y-axis and include the equation for the fits. Then make a third graph of this data by putting the launch angle listed first and then listing the range values for the range without drag, followed by the range values with drag. Highlight all 3 columns before choosing to graph them. This should make it easier to judge the effect of wind drag on the range of these same launch speeds. Note, we are not linearizing any graphs this time. You may find the 2 videos for graphing using Excel useful, as they also show how to do fits to parabolic data as well as how to make sure your origins for the latter 3 graphs all start at 0. Calculations. You're going to be creating a range equation. This equation should give the range in terms of the initial velocity and a single trig function of the angle the projectile is fired. This is a proof that can be completed using the proper kinematic equations applied to both the horizontal and vertical motions. Chapter 4 in our text has a section on projectile motion that might prove useful. Now, I am well aware of the fact that there are millions of websites out there that will provide you with the steps for finding the range equation. If you choose not to do this derivation yourself, but you get the answer from a website, that is fine. Make sure and include the website as part of the derivation. In other words, cite your sources. Do not put a derivation in your write-up that you got from some other location and not give the credit to where you got it. That is plagiarism. We do not do plagiarism, but you must list all the steps, not just the result. What you should submit: in addition to completed data tables and answered questions, there are 4 graphs. The magnified version of range versus launch angle, the 2 separate graphs of range versus launch speed, one with no air drag, one with air drag, and the graph of the combination of the 2. And there should be a calculations page where you provide the proof, starting with the appropriate kinematic equations, leading to an equation for the range of the projectile as it is related to the initial velocity and a single trig function of the launch angle.